is my neck of the woods. I was like, they had what I enjoyed walking around with their campus. They had talking trash cans.
Talking trash cans.
They had sensors
at MIT.
Yeah, they had sensors when you walk by, and they like remind you to do this, or they'd say like something nice or like a little joke.
Yeah, I love that. And so, Mr. Alexander,
yeah,
let's get into this article. And I know it's a fun article, and I hope we can explain it so that everybody understands. I had to read it 3 times, but this is really, really cool if you get the basis of it. An important quantum algorithm may actually be a property of nature.
Yeah, this is fun. So Bell Labs in Jersey, and they've done a lot of very interesting stuff for the public, and 99% of the work has gone towards like black budget programs. Total side note, but quantum computing's been quite interesting, and it's been around a lot longer than you think it has. So what's the first year date we have on this?
We have 1996, sir.
1996 is when they were working with the first quantum computing machine. Now, the idea with quantum computing, like with all computing, is
this is when Bell Biv DeVoe was popular, Paula Abdul.
Isn't this amazing?
1996, think about that.
And these guys in Jersey are like working with quantum computers. And that's Bell Labs.
Yes.
So I wonder
Tupac.
I wonder how long quantum computing's actually been around, if Bell Labs privately got it before the government actually had their hands on it. DARPA had the internet, in the 80s?
Well, there's quantum computers. I mean, we have one
10
minutes away, 15 minutes away.
Yeah. So here's the general consensus, the general thought on this. When we look at data, it's stored in a specific format. Now, in the end all be all, it's a list we have to go through. We have to process a list to look for something. The computer starts at the top, if that's how the algorithm is, and then runs right through the bottom until it looks for whatever that key marker is that says, I need these characteristics, pull it from the list. Find out where that entry is.
That's why speed is so important.
That's why speed is so important for this. Now, with quantum computing, you're looking to solve for an n, a large n, a number of entries. So you have a volume of entries. But what's the most efficient way to search for that thing? Can I search from both sides at the same time? Maybe 3 sides? What about 4? So here's the concept that they took on, and I hope I can put this down in layman's terms.
Mr. Grover.
Electrons, they look for essentially flaws in material surfaces. So say I have a sheet of metal. It looks flat to us with our human eye, but when we get down to, very deep microscopic levels, there's divots in this. And the bonds of these electrons floating around, they're looking for a home. You don't want just free electrons flying around, right? They want to like attach to something. So these little holes, what it does is the electron has to search across the surface of this metal plate. So it kind of, there's my little hole. Here's where I want to sit.
Right.
Okay. And this information for how it got to this hole is happening on a quantum level. It's a thing called a qubit, where it's like you have 2 things happening at the same time, 2 different states happening. It's searching, and while it's searching, it also has its own like rotation and other things of that nature. So it has the ability to efficiently solve, depending on the number of sides or whatever the surface might be, or if it's a table of data, well, how many different characteristic sides of this table of data do I have that I have to search through so I can find that little hole? So the material world that we work with, from a quantum sense in the electrons, like go here, can we put that same sort of algorithm, quantum algorithm that an electron is using, and apply it to searching for things within a table of information?
So we're going to nature to find an answer.
We're going to nature to find an answer. But what they found is that as the mathematics of this, mathematics of, surface analysis and things of that nature have been brought in, they've realized that, it's not really so mathematical. It's more of a natural occurrence that is occurring. So it's like we found that this mathematical formula, this quantum formula, if electrons are efficient at finding these holes, why couldn't that same thing happen with us finding a piece of data? That's the efficiency of quantum computing. So it's not about how fast it can do it, but it's just like, it already knows how to do it. And it can do it from 2 different phase states at once.
Yes.
I hope that is making sense.
Yeah. So let's drop back and we're going to work to the article. I think that explained it very well. So 1998 was the first scalable version of this.
Yep.
So that was when the quantum computers were in full effect, 1998. Then it wasn't until 2017 that it worked with 3 qubits.
Yeah, with 3 qubits, which is saying I can work with 3 different states, that are happening at the same time. And a qubit is 2 states. So it's essentially 6 states,
Right.
6 different vectors, I think, is what's happening. I'm not a quantum physicist, but I believe that's what's going on. And I say believe because I'm pushing my knowledge toward the article.
Right.
But with the quantum computing, you have to maintain a world that is extremely cold. And this will tee up into further part of the article, because when things are cold, it slows down, anything else atmospherically or disturbances that can come in, right?
Yeah, and the University of, I hope I pronounce this right, Toulon in France, said that they took Grover's, because that was the person that started this quantum physicist in 1996. They took Grover's search algorithm, and that's when they began to find that there was a naturally occurring phenomenon. And this is what they said. We provide the first evidence that under certain conditions, electrons may naturally behave like a Grover search, looking for defects in a material.
Yeah, remember I said
Right.
It's looking for a defect in that plate? That's what the electron wants to do. And there's certain vectors. And when I say a vector is like a position of something, like directionally within a 3-dimensional space.
But picture, like you said, a big square metal sheet, and then you have a quantum, how it walks across the surface.
Yeah, it's like,
quantumly.
how do you watch that electron?
Move
Nature
across
is
that
so
surface.
nature's so efficient.
Right,
So how do you watch it trace its own vectors to find that hole
right.
or that deformity?
And to us, it would look like it's randomly happening.
But it's really not.
Right.
There's a high amount of efficiency, and what's been paired is that this quantum algorithm for quantum computing, right? This idea of searching also matches what is naturally happening in nature. So then this begs the next question within the article. Quantum computers are albeit extremely cold, but what they're finding is that this 4-sided structure of a square, searching across a square with, 20 specific outputs that can happen with it, is the same exact thing that you find in DNA with the nucleotides and amino acids.
Mm-hmm.
You have a 420 rule, right? So
Not
the
the Dr.
420,
Dre.
yeah, not.
Glad he's okay.
Yeah.
Did you hear he went in the hospital?
Are you
Yeah,
serious?
he had a brain aneurysm or something.
Oh, that's terrible.
Yeah. So let's, before we get into the DNA part, this is really interesting. So this is a search of 2-dimensional space, and the nature of the surface has the important influence on the search. So we need to understand that. So one type of surface consists of square grid where the quantum particle has 4 possible moves at each vertex, which you talked about that. But what is interesting is how it explores the paths compared to how a traditional computer would look at an Excel sheet and then go from 1 to 10,000.
A traditional computer is going to say, here's our first thing we got to search.
Let's search this database.
I want you to run every single path on it.
And then you could do the Control F,
Yeah.
find, and then you're looking for the word that says bank.
Yeah. So, okay. So first thing, we're going to run through them all. No, that didn't hit. Okay, go to the next one. Run through every single piece of processing again. No, that didn't work. Go to the next one. And it'll do this tens of thousands
And your process
of
is
times
going to
over.
be at 90% wide searching.
Yeah, and it's just melting your Intel chip in the inside. And so what they're saying here is like, that's not a good way of doing it. If we realize that we have a 2-dimensional system of storage of an X and Y vertice in how we store things online or on servers, well, that's the same exact function of a 2-dimensional space for an electron going across some sort of material surface.
Right.
There's no reason it can't be applied in the same sort of efficiency to search.
Yeah, and I like how they got crystals involved.
Well, yeah. Well, crystals are interesting because if you look at everything in this world is crystalline in
Right.
nature. I don't want to get too much into this.
I'll stop you.
Yeah, please. But what
Go down the Alice
what
in
you find is
Wonderland hole.
everything has a very geometric structure at that level, right? It's a crystalline lattice. Metal has it, our bone has it, everything has it. So finding out how to efficiently search across all of these different crystal lattices also shows, that electron path, and it fits extremely well with what's going on a material surface, what's going on in a 2-dimensional sphere. And if everything is crystalline in nature, which they're telling you here in this article, which is true, well, then my DNA with its nucleotides and amino acids is also crystalline. It has a specific geometric structure, right? Whatever it is for DNA. That helix, the way it's linked up,
Right.
that has a specific geometry. So the electrons and how things move in that phase state is much like what's going on with this quantum computing state. in these electrons. But here's the defying part of this. The computers are operating in a realm of, sub-zero temperatures, very, very cold, like maximum cold, so that you can get, the quantum material to move efficiently, like up in space in a vacuum. But that doesn't make any sense. Is our DNA ice cold? No, we're in a warm organic body. So then that defeats this thought that quantum things could only happen in this vacuum cold state. Well, then how is it possibly happening? The same rules that the electrons are bound by in their quantum state
yes.
for going over these surfaces are the same exact 420 rule that is happening with the nucleotides in our DNA.
Yeah, and they said this, the results are eye-opening. The question they ask is how quickly an electron can find the hole in a grid.
Yeah.
And then so the big breakthrough is to show that the simulations reproduce the way real electrons behave in real materials.
Which is fantastic.
So
we're not designing...
We're using nature to help us search better.
Yeah,
rather than machine learning and AI is going to take this
yes,
and turn around, and it's going to create a huge uplift. Because this article is more important than people think.
It's not saying that we search better than nature.
Right.
It's that we're using nature for the most efficient searching process. This creation we're in, has spent so much time evolving itself efficiently. If it was inefficient, the thing would collapse in on itself.
Well, think of it this way. You have this crystalline form, and then you have these electrons moving across that, trying to find the weakest link. And then either say, cells, you have to eradicate this, or what do we do with this? But it can search and find that at the most efficient possible way.
Yeah.
So why wouldn't we just copy nature like we should in everything we could? Shout out to the pioneers that are out there.
Yeah, shout out to all the pioneers.
Yeah, because I love them and they're our future. And I read everything. If you have not gone to YouTube and typed in Bioneers, you should. But this right here is another prime example of understanding nature, implementing it, helping us find an answer, solving humanity.
I love that.
Yes, and
I
so
love that.
I don't want to get too heavy into this article. We can get a little bit into the between four alternatives in a single step, which is four is the optimal number. The nucleotides, we talked about that, defines a single amino acid, sequence of triplets.
Yeah, so those 4 steps, you've seen this logic is very old. The Greeks actually came up with this. You have 4 different states of agreement. You have yes, 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 no, 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 and no, yes. So there's what you think is binary actually has 2 more paths, 2 more states that can happen. You can be in agreement, but an agreement towards the negative. Yes. Or you can be in a negative with absolutely no agreement. So it's like the electron has a spin and a direction at the same time. It's living in 2 separate states. So our logic works that way also. But now we're just applying a natural logic to what is actually happening here in this sort of quantum computing environment.
Yeah, and then here's the part that upsets me. And I hope, and I want to, at the end of the article, it talks about the negative aspect of it, if you want to say it's negative. I think there's just some bridge building that needs to happen. So when Patel, a scientist, published his idea, quantum physicists immediately, the article said this, poo-pooed it.
They're jealous.
At the time, they were bogged down in their own attempt to control quantum. They're trying to control quantum processes. That's what the article said.
Wrong word.
Yeah, wrong word. The obvious problem, they said, was that living things operate in a warm, messy environment in which quantum states would be immediately destroyed. You talked about that. Now, the biologists were equally dismissive, saying that quantum process couldn't possibly be at work inside living things.
Why is everyone such a disparity?
So we have quantum physicists upset at this truth,
biologists,
creational truth, and then we have biologists upset
and
about
then you
it.
have a mathematician that sits in the center who's working strictly on rational logic,
Yeah.
and he's like, well, you're both wrong. Can we come together? Can we come together, please? Because this is obviously how it's occurring.
But what creates? Because I want to end in this. And this is a question for you, Mr. CEO. What creates this dogma that we're a biologist because it's not biology, or a quantum physicist it's not quantum physics? What creates this dogma towards data, and how does TARTLE solve that with its marketplace?
A lot of these scientists believe that they live in a world of isolated systems. It's very hard to work holistically, and when you have a lot of inputs, it can really alter what your hypothesis is for something that you're trying to solve. Because you think, I have 2 inputs, this is my direct output. But what we see in nature is that there's an infinite number of inputs. So when they say, something's crossing the line into their area of research, this whole new input, it begins to debase all of their work they've done for the past 40 years in their career.
Their white papers.
Do you think they're going to become? Do you think they're going to become a little defensive?
Oh, of course.
Most definitely. And they are going to poo-poo it until the evidence becomes so strong that it's like time for you to wake up and drop your ego. And when you look at data, data's agnostic. What this mathematician is saying is like, this is just what it is. We've observed it. It's not that we're saying, oh, it can't happen because we're biologists. That's not true, right? Or it's like, oh, we're quantum physicists. Well, that can't possibly work because we're quantum physicists. Well, the guy's strictly observing data for what it is. So when we look at TARTLE and just saying this is the data, it removes that whole world of polarity that is just like this false perspective of existence. It just destroys egos, and it really hurts people inside until they learn that the truth can be a little uncomfortable for you because you've been living in this world that's a lie. And when we begin to focus on this collective amount of data for solving these problems, well, here's the truth. You actually screwed up. You had it wrong. That's just what it is. And it's time for you to learn from this mistake. Observe what you've done. Look at your system of cause and effect. We appreciate that you're a scientist, but the world is not so isolated in a little box that you think that it is.
I love that. And one of the things that I want people to understand, whether you're a buyer of data, which you can at tartle.co, or whether you want to sell your data, how simple is it to sign up?
It is so incredibly simple to sign up. We didn't want to have a lot of friction for you to get into this process. So you go to tartle.co, you click on the button that says Get Started, and you're going to put in some very basic information. And you're already going to have that account created in 30 seconds. And then we're going to hold your hand, and we're going to walk you through this new age process. We're going to walk you through what the future looks like so you feel that same vision that we feel. And then as we do that, you're going to understand very well how the system works and how this tool empowers you to do a lot of great things.
Last question, we'll close out in this, then we'll hear the outro. Why is it important for humanity to sign up for TARTLE?
It's important for humanity to sign up for TARTLE because we have a lot of problems that we're facing. We have a lot of ideologies that disunify us. We're collective on a single closed system planet. And it's important that we work together in a coexistent behavior to figure out these problems that we have created. No one else created it. We're doing it. And so if we can come together with our data, unify that, and solve these issues, that's the most important thing that could possibly happen with this. That's a positive future for us all.